also thankful for Gabo overview and embedding the whole thing about some of our latest results using these machine learning models. Before I get there, I should include a lot of the hands-on work. So, in particular, I should mention Raghu Ramakrishnan, whom some of you probably know or remember. He's a professor now in India, and he generated the molecular training set. I should also point out Bing Wang, also who quite recently joined my lab, PhD student who did some of the representation development, and Anders Christensen, who is also involved in developing the methods based upon which some of the results I'll be showing now have been produced. So our approach to this is that we like quantum mechanics. So in a very maybe inappropriately short way of summarizing it, we have this equation which maps coordinates, configurations, and nuclear charges to some eigenvalues, And, so this eigenvalue problem, we'd like to, we know we can solve this with the usual methods, with the usual approximations. And what we really started to think about is how to do this using machine learning. So to go from nuclear charges and coordinates to eigenvalues or observables in quantum mechanics. And this is something which, so in 2011, I organized a workshop at this Institute of Pure and Applied Mathematics in California. It was on chemical space. And this is actually, like many things, it's Matthias' fault, because I was at a workshop he had organized in 2005, and that's where I met him. And I realized that this institute is a great place to start off new things. And this is then where I also met was not only Alex Tkachenko, whom I've been collaborating ever since the 2005 workshop, but also Klaus Müller, who is a machine learning expert at TU. And we had this discussion of how to do the same thing as the traditional way of solving Schrödinger's equation. And so these kernel methods, Gabo so eloquently summarized, seem to be the appropriate thing to start with for us as well. So this was 2011, the GAP paper was out for 1 year. And so we use basically the same approach, only that our training set here is different compounds. So not different configurations, but different configuration and different composition. And then we followed the same scheme, so this is something I've already explained. In order to do this, of course, you need a certain representation with which you can quantify the similarity. And the thing that we came up with was this Coulomb matrix, where on the off-diagonal elements between, so it's an atom-atom adjacency matrix, which is the complete information which you have, and we place a Coulomb term on the off-diagonal, and the Coulomb repulsion between the nuclei, and hence the name. Now this is quite an interesting representation, because it turned out later on it's not the best representation, but it's a very decent baseline model for our sorts of applications. So we view it as the LDA of machine learning for our were other variants of this when chopping, taking elements from here and bagging them, and there are pros and cons on both. Now, before I enter to our results, I'd like to stress a little bit an aspect which really convinced me that this is a good direction to go to. And that's this difference in terms of fitting with respect to what we've been doing traditionally. So, if you wish, when I was a student, this is how I saw the fitting problem. Either you'd be under-fitting, you'd be just right, or you'd be over-fitting. And the same information is shown here. If this magenta curve is your error on your training set, and the red one on the test set, then there is some optimum where your functional form permits you to have the best compromise. Now, I would argue that the difference, or one of the main differences to what we do now with machine learning, is that we don't follow this paradigm anymore. Rather, we have a situation where we don't compromise in between the data, like shown here in red, traditional way, but rather we truly interpolate the data we have. We just want to make sure, of course, that there's no high oscillations in between, but that's quite straightforward to do. And so it's really just much more an interpolator than anything else in my mind. And that has the interesting effect that then on your learning curves, your test error, because your training error is zero. Actually, we use this as an important test when you want to debug your codes to test that your training set errors is zero. So this is zero, and this just pulls down the test error down to arbitrary accuracy. And this is something which is actually well known in statistical learning theory. So you can look in these papers from '94 on the Butnick book. This is by Butnick and co-workers. And in his book in 1995, or Klaus Müller also pointed this out in '96, that really you have a prediction error which should decay inversely with polynomial with training set size. And that means you should be plotting a log-log curve, and then you get a linear behavior of a good model. And a bad model will not have that behavior. And this is a very easy and convenient way also to compare different models. So this was already pointed out then and suggested that it should be used. Now, one interesting thing of these kernel methods, which is quite straightforward and appealing in my mind, is that there's a funny analogy to quantum mechanics. If you remember the expectation value, the energy for which your variation in your wave function, this is the variation principle gives you this wave function. And that principle you apply to the Hamilton operator. But when you want to calculate another observable, you just use that wave function and with the corresponding operator, and it spits you out the. So it's always the same wave function, right? No matter your observable. Now, if you train a machine learning model on a bunch of molecules or compounds or solids or whatever, you'll have a kernel matrix, right, for which you need to invert to get your regression coefficients. Now, then you can, in this training equation, you can invert that kernel matrix once, and then you multiply it with the various reference properties. This means your kernel matrix really doesn't change as you change the property. And so this is similar to the wave function. Right? The wave function also doesn't change as you evaluate your property. And so what changes with your property is through this multiplication is just the regression coefficient. So when you look at this expansion, in some sense, the alphas represent the observable, and the k is your underlying variable. These are results which demonstrate this. So we have various electronic properties on organic molecules, and we have these learning curves. At each training set size, we have one and only one kernel. It's always the same kernel. You have to invert it once, and then you multiply it in with all these different properties, and you get these errors, and they go down linearly on this log-log program. So that is something which numerically confirmed this idea. Now, our philosophy is, and this was pointed out two weeks ago at this SIGAM workshop organized by Luca, that there's maybe a little bit of two philosophies in this, that how you approach your representation. And one is to become very agnostic and say, we don't know what is important and how it should look like, and we use it as a variable for your machine learning model. And so we throw in everything we can think of, and then we let the machine optimize the particular selection of features and their functional form. And this has resulted in very convincing numerical predictions. It's sort of heuristic. So Gantian pointed out in his talk. Now we go a little bit the other way around. We say we follow Occam's razor. So we really want to include only the bare necessity. And so I show one example for solids. Most of our results come from molecules, but we have solids on our horizon. This was a paper where we sort of tried to push this principle to its limit. We took the apacylite crystals, also mentioned by Gantian, and they live on this cubic lattice, and we populated. They're quaternary. It's the most frequent crystal in the inorganic crystal structure database, and so they are. You can think of them as a vector which contains, for each elemental type, it contains the coordinates in the periodic table, so the group and the period. And since you are looking only at the apacyllites for this one crystal structure, you don't need to specify coordinates. It's implicitly in that information. And so if you train the machine just to apacyllites, it's perfectly fine. It's within that domain that the machine will work. And this is something we could show. This is the out of sample prediction error coming down on this log-log curve for the formation energy. And we reach 100 milliev per atom after training of 10,000 apacyllites. And then, of course, you can turn around and screen all possible apacyllites. In our case, there were 2 million apacyllites, so you're looking at 2 million energy estimates with an expected accuracy of what DFT would usually give you, so roughly 0.1 eV per atom. Now, of course, this is what makes the whole thing exciting. With DFT, this would have taken you 20 million hours, and with the machine learning algorithm, it was less than a day. So you see one component here. This is the second component. And each box then has a third and a fourth component. So it's a 5-dimensional. Now, let me go to these molecules. So Raghu calculated for 134,000 molecules, which we drew from an organic chemist's list of reasonable molecules. So he made that list with graphs, smile strings for billions of molecules, and we took the smallest ones which had up to 9 atoms, not counting hydrogen. And there happened to be 134,000. We did DFT calculations for them, and we calculated. We got various properties, including the energy, HOMO, LUMO, dipole moment, polarizability, gap, obviously, heat capacity, and the highest fundamental vibrational frequency. Actually, we got all frequencies, but this is what's shown here as a distribution. It's normalized by maximum property, right? So the dipole moment is really the norm, so it's always positive, and that's why it's so skewed. An interesting thing is organic chemistry, Louis Vermont pointed out, and I believe it also applies to solid other phases. that enumeration surpasses imagination. Right? So if I gave you this composition C7O2H10 and asked to draw all possible molecules, this is a task, it's hopeless, right? So here's an example for these molecules which are present in the database. We plot here the enthalpy of atomization in ascending order, and just if you zoom in this area, in this linear regime, you see that there's roughly 100 molecules in an energy window of 1 kcal/mol. So that's 0.05 eV. Where you have 100 molecules, right? And they look really different, right? So this is really, yeah, I doubt the humans would have the imagination to draw all of these. I'd like to tell you now about some of our recent results. And to start off, we studied a lot, we spent a lot of time on looking at the representations, the role of the representation. And what we found, and this was just accepted in JCTC, it should come out pretty soon. Actually, I think it's already online. What we found is that the error, the prediction error, can be crunched down to such levels where you systematically surpass what we typically expect for the function theory. And this is shown here. It's a collaboration with Google, and these Google engineers, of course, they want to apply their Facebook or their social media algorithms or their ad placing algorithms. They want to apply this to materials and chemistry. So what you see here are various regressors. KRR is kernel rich regression, random forest, GG and GC are convoluted neural nets, so this is what goes as deep learning. And here you have various representations of the molecules, and these are results on these 134,000 organic molecules. Various properties are already mentioned. What you see in dashed here, these horizontal dashed lines are what we typically expect as DFT accuracy. And you see that for every property, there's at least one model that surpasses DFT accuracy. So I don't think it's a stretch to say that we have numerical evidence that machine learning models go beyond DFT. And that, of course, raises important questions as to what else should be used then for training, right? You're certainly not going to eliminate DFT, but DFT is no longer enough. Now, this is one of the most successful representations in here. It's a simple histogram of distances, angles, and dihedrals in your molecules. So this is sort of, supports this Occam's razor philosophy that that's sufficient to get there. Now we looked into this in more detail, and here's a little exercise. If you construct a kernel model of some function, let's say a Gaussian function shown in here in red in this inset, you want to model that Gaussian function, and now you plug in all sorts of families of functions as representation. What would you expect to get in terms of performance? So this is something you see here. You see the learning curves for various functions. You put in a quadratic function, actually you don't have learning, it's not unique, so you cannot resolve this noise anymore. And you don't have learning, it's flat. If you put in a linear function, you get this learning curve. If you put in an exponentially decaying function, you get the dash. It's hardly distinguishable from the linear. But as you go in the exponentially decaying function and you change the exponent of x, so if e to the minus x to the power of some exponent, this is what you see here. These are these exponents, right? So for one, you're just a conventional exponentially decaying. Then you have minus x to the 1.25 beta, 1.75 beta. You reach 2. So this is a Gaussian. You use a Gaussian as a representation to model a Gaussian. You get the lowest lying curve, and then as you raise the exponent further, it comes up again. So this would suggest that the closer your representation to your target, the better your model. Now, we wanted to see if this also holds for molecules. So we used the Coulomb matrix, and if you look at the 1 over r term, of course, you can put in an exponent here, and by changing the exponent, you can modulate sort of the physics in this. And the first thing we wanted to see was actually if we can make it worse. So fundamentally, to say as atoms dissociate, you have less interactions. That's a very qualitative fundamental physics in there. But what if you do the inverse? If you say as atoms dissociate, the interaction grows. Right? That should be even further apart from reality than anything we had. And sure enough, if you put a -1 here for the exponent, so just proportional to distance, your learning curve goes from, this is the Coulomb matrix, and goes up. And if you make it quadratic, even worse, it gets up even worse, even more. Right? So this is an interesting exercise. And then, of course, you can look at different exponent layers, and you see the lowest learning curves for 4, 6, or 8, so sort of long non-dispersion or dipole-dipole sort of laws that seem to be to model the surface the best. And this, of course, then we thought, okay, well, what is the best approximation we can have for the potential energy? And we took this universal force field, which was published in the 90s by Goddard and Rappel, and we included bonds, angles, and torsions using these parameters. And what you see here is bonds, angles, and torsions, learning curves coming down systematically on these molecules. You just, for reference, is the Coulomb matrix involved. Now, you can do this for other properties, and you always see the same trend. It always systematically improves. You can look at outliers. These are the worst, right? And as you add bonds, angles, and torsions, their error comes down systematically. You can look at the average contributions from each of these many-body terms in your representation, and you see it also decays as you would hope for. And this all was shown just for these isomers. We also showed this for all 134,000 molecules. You always see the same sort of trends and physics. I'm going to skip this. Now, this was published last year, and since then we've been trying to improve this further. And some work, Gabor and Michele Ciotti, and also James, here present, recently published, is shown here. So the HDAD was what I showed you from Google, the Google collaboration, where we trained on 90% of the 134,000 molecules, and this is the error in EV. And Gabor could show that this soap kernel with Michele gets better with less training. So that's very exciting, and they have a learning curve. And now we recently, so we've been working on improving our model away from this Bammel towards something with less parameters, again following Occam's razor philosophy, but possibly with better physics. So, this is this new model, and this is shown here for a small data set. But if you apply to the big data set, it's sitting right here. And we can also make a learning curve, which looks like this. And now, so we are a little bit having a fun race going on between Lausanne and Basel now. So Michele is pushing for a multiscale model, which comes down again. It's the black one. So you're roughly at 1 kcal per mole, so your 0.05 EV limit with 1,000 examples, right? And that's also roughly where we are here. So this black and our red should be basically converging. converging towards the same. It's very exciting. So how does our approach work? I cannot tell you too much, but it's super exciting, and here's just in a nutshell. We expand the whole thing in this many-body approach, and we construct these distributions such that the integrals can be solved analytically. And so this makes the construction of the kernel matrices very fast. Here's a free-body example for this innocent molecule. If you look at oxygen and its free-body interactions with the CC pair, the HC or HH, this is how it looks like for the oxygen. And then you can do the same for carbon and hydrogen and so on. You do this for every atom in your system. Okay, since we have this, so we've been mostly working on molecules, but we follow the idea of quantum mechanics, so it should be universally applicable. And this is now results where we tried this latest representation on solids. And these are random solids from the materials project. So random composition, random crystal structure. The crystal structure symmetry doesn't really matter because it's an atomic representation we are using. And all you have to do is expand your unit cell to include enough images so that your atomic representation is converged. Now, if you look at this with 3,000 crystals, we are roughly at 100 millieV per atom. Just to remind you of the apostolites, we needed 10,000 to get to this level, and this was only applicable to one crystal structure symmetry. Okay, so we've been pushing these developments further, and another variant of the representation, which is already out there, is what we call the ace-latum. It's an atomic, spectral, London extrarotellar Muto representation. So we really put the London and extrarotellar terms in the representation, and also this produces very promising learning curves, as you can see in these curves. And we've been using this representation in a paper which we just very recently posted on the archive and submitted, and we are extremely excited about this. So and you're among the first to hear about it. So I'm still this is still new for me in presenting this, and I think it's really awesome. So what we had, and this we've known for a long time. So Jörg Behler pointed this out, Gabo pointed this out, and many people have that you have you can use an atomic representation. And that means in principle you should be able to make this thing scalable. Right? And that's exactly what we are trying to do here now. So what we do is that we say your typical kernel model, when traditionally we had a kernel here which would compare entire compounds, now we replace that kernel by a sum over atoms, and this sum runs once over your atoms in the query compound, let's say something like this, and it once runs over your atoms in the training compound. It's a double sum. Now, training compound and query compound do not have to share the same number of atoms. They can have very different number of atoms. And that's what we are doing here. Basically, your number of atoms in the query can become very large, like this one, and the number of atoms in your training reference can remain very small. And so then you're comparing small reference compounds to individual fragments in your molecule. And you can, through the kernel regression, you can connect them all with the proper weights as regression coefficients. And you get an estimate of a large query compound. So, since this is really based on this idea of an atom and a molecule, we baptize this the aim on. And it just so happens that it's also associated to funny pictures like this on the internet. You can think of this as an extension of the periodic table where you include the environment for each element. And so we want we want training sets consisting of these fragments. And then you train your coefficients on those to predict a new query. Now, let me illustrate this. Suppose you want to predict something like this here. What we do is to run through each atom, and we do a subgraph matching, where we say, okay, what are amines that resemble this fragment? And so this is a very rapid selection of these small fragments that you need for training. And for this molecule, here are the corresponding amines ordered by size. So this is 1 atom, 2, 3, 4, 5, 6, 7. And then you see the error on the query prediction of this. This molecule has 9 atoms. You see the error shown here in black for the atomization energy. It changes sign, right? So it comes down from above, and then it crosses 0, and then it comes up from below. What's also shown in red is a different property. This is the polarizability, which also approaches the target level. So this is just an illustration. And then, of course, we were excited to apply this to huge molecules. And so there's a very busy slide. What you have here is the model prediction versus truth. So we use B3lib as a reference for DFT. And this is the atomization energy. So you have a very large scale here on these axes. And there's a whole bunch of molecules, I think 20 molecules or so. And what you see here as legends of different colors are the size of the amines we used, right? So if you only have one, that would be just these two guys. If you placed saturated atoms instead of connected atoms, that's the worst you can do. And the error of all these, so in brackets you see the error shown taking average over all molecules, right? So your error is huge. Now if you include 2 atoms in your amines, then you have bonds. And so your error comes down. Right? If you include 3 atoms, then all of a sudden you have the angular information. Right? And that's very important. So then you come down again. And this, I would argue, is sort of, this is a force field level of accuracy. If you include 5, you reach a GGA DFT level of accuracy. If you go to 7, you are at chemical accuracy. Now, 7 atoms is a benzene plus something. Right? And imagine we have that, and for something like Taxol, one of the most important anti-cancer drugs, you can make a very good prediction of these huge molecules, right? So we are really excited about this. And so I'll show you some more. We wanted to see where it works, where it doesn't. So we have a couple of systems where we tried this. These are polymers. You have the usual polyethylene, polyacetylene, not shown, but here are 3 more less usual molecules, polymers. And you see as a function of, so this is number of amines, right? So with less than 300, you can get this polymer with chemical accuracy. And the numbers in here show you the size of the amines. So you have 300 with no more than 7 atoms you need for this, right? So this is also very important, right? Because as you grow in size, the dimensionality of chemical space explodes. And so you could not possibly, and also the cost for calculating doing your reference calculation grows with the number of atoms, obviously. And so it's very important that we can get a handle on the size of the molecules in training, or the size of compounds we need as well. Now, we can also apply this to intermolecular interactions, and these are water clusters with from 11 to 21 waters, which we predict, and we use as a training set water clusters with up to 10 water molecules. And, in total there are up to 7 clusters, right? Up to 7 clusters with up to 10 water molecules in them. So suppose you have 7 clusters with up to 10 water molecules, you can predict the one with 21 with with chemical equivalency. So we see this systematic trend working throughout. We can also do surfaces, 2D materials. What you see here is a doped HBN sheet. And as you grow the region around the dopant, these are your amines here, you see convergence of the atomization energy. And finally, we can also do silicon bulk. So what you see here again is the error on the atomization energy as a function of number of amines, so we need up to 5. And in here are shown the number of atoms in your amine. So it goes up to 18 atoms, so something like this here. This is the amine with 18, which you need to get this down to chemical equivalency. Now, in these crystals, you need to go quite far to capture all the non-local effects, but because of the symmetry, you have very few amines only to deal with. Then we did something, so this you shouldn't actually do. We did a lattice scan with this model, trained at the DFT relaxed geometries, right? You see in red, this is what the model gives you. In blue is the DFT curve, and in black the experiment. So finally, you can wonder what do these amines do? How do they work? And for this, we did an analysis on these organic molecules, and we took 11,000 out of these 134,000. And we made predictions for all of them. What you see here is the average error on these 11,000. So we have a variance here. And because the training set is different for every query, you also have a variance in training set size, so an amine set size shown here. Now note though that this axis is tricky. It's not like the previous learning curve because your training set is different every time. So it's the number of amines per query. This shows that your variance, your error comes down systematically with amine size, and typically with 6 or 7 in size, you're coming really down to chemical accuracy, and typically you need less than 100 amines to make a prediction. Now, what's interesting in this 134,000 set, we can look what are amines which would be required to cover the entire space. And what we see is shown here in black is the frequency of the amines as a function of their size. So for how many of the organic molecules would you need amines of size 1, basically for every one, size 2, 3, and so on. And you see that the frequency becomes less and less pronounced, and the least frequent amines with 7 atoms look something like this. So they occur, you would need them just once to predict one of the molecules in this organic data set. In total, there's something like 20,000 of these amines. You go up to 7 atoms. So this basically means with roughly 20,000 small molecules in your training set, you could cover all of organic chemistry. Just for comparison, in blue is shown how the number of possible molecules, so organic chemistry space grows with number of atoms. Now here it's shown for 3 different query molecules. These are the amines to get their energies with chemical accuracy, and some of them are shared, of course, right? And so that's really appealing because those are the ones which you only you get twice or many times your buck's worth by sharing, recycling your training set. Right? And so all 3 of them share these. These 2 molecules share these, and these 2 molecules share these. And by the amount of how much they share, this overlap of amines is also a measure of similarity, right? So chemically speaking, they consist of more or less similar fragments. So it's very intuitive of what you would expect also but now it's put into a quantitative model. Since the Amen model is also atomic based, we can print out atomic energy contributions. And those are these numbers shown here. And sometimes in brackets, when appropriate, we also show the corresponding numbers you would get from a force field. And you see that the scale of these numbers, so this nitrogen, for instance, the Amen predicts this number, and the force field would give you this number. This is very similar, right? And if you look at carbon instead, it's 160 or so, and also the force field is. So we recover sort of the previously known physics. So since these Amen libraries are interesting, and since you have these wonderful glasses, I will show you a movie which was taken in VR. In principle, with these glasses, you should be able to see this. These are the 1,000 most frequent amens for organic chemistry. If you watch this with these glasses, actually, you risk of getting nauseous because it's so. So this is a 10 times 10 times 10 matrix of what we think is the dictionary, the most important words in the dictionary of organic chemistry. And finally, an example of how this also looks for intermolecular forces. We have looked at the Watson-Crick DNA-base pair of guanine and cytosine. You get, so this is the atomization energy error, right? So it includes the bonding. It's not the intermolecular interaction energy. And these are all the amens you need. And it's quite interesting. So the A are the amens for this moiety. The C are the amens for the cytosine. And B are amens that are shared between the two, right? So these are shared. And then in order to get the hydrogen bonding, you will need these additional amens. That's what takes care of the hydrogen bonding. And it's quite interesting because none of these amens actually needs the entire ring. You get the ring delocalization effects, which are strong in these hydrogen bonds. They are known to be very important due to the high polarizability of these moieties. You get those by adding so your summation of the kernel takes care of that, and the inversion of the kernel introduces the coupling. A little bit like the multi-fidelity model, right? So you can connect different physics through the kernel. Finally, an outlook, you can of course use these amens then by distorting them and getting forces. You can learn those forces, and so this is a relaxation using an Amen model-based force estimator. So this molecule is being relaxed using as training sets only smaller molecules. Right? So this molecule was not in training. If we can relax it, it also works for water dimer. And for this molecule, this is the initial deviation in coordinate, and we stop the relaxation then. That's what I wanted to tell you about. Thank you for your attention.